Okay, good morning, everyone. How are you doing today? Let me know if you can hear me. Give me a thumbs up in the chat so I know. Okay, thank you. Or on Gathertown, wherever you give thumbs up, I guess. Right. So we're going to continue today with discussion of static equilibrium, and then maybe, although unlikely, we'll get into elasticity and stress and strain. Um, so we identified last time what the conditions are for equilibrium, for static equilibrium, and that was two conditions. One of them was that, of course, all the net forces have to add up to zero, so we have no linear acceleration of the center of mass, and then all of the torques have to add up to zero. So we don't have any angular acceleration of the object of whatever rigid object or collection of points we look at. So we looked at one example, I think, last time. So we're going to look at a second example now, which is this, a typical example, I would say, of the torque balance. So it's a meter stick, which is in this case 1 meter long. And if this was actually in class, we would be able to actually demonstrate this in class, and we can do this example as a demo. But of course, that's more difficult, and it doesn't really work as well on online. So we have a meter stick that's balanced on this point here. That's at 70 centimeters from one side, 30 centimeters from the other side. The meter stick itself has a weight. It's 150 grams. But there's also additional weights hanging off of this meter stick. There's a weight of 50 grams, weight 1. There's a weight of 75 grams, weight 2. Weight 1 is hanging at the end. Weight 2 is hanging 30 centimeters from the end. And so the question is, what weight do we have to hang off this balance on the other side, 30 centimeters from the pivot point, to make sure that this entire torque balance is in equilibrium, in static equilibrium. So it's essentially not starting to move. What would happen, of course, if it is not in equilibrium, then there will be an acceleration, both an angular acceleration. Let's say we pick mass 3 too heavy, the angular acceleration will start to move in the direction, the negative direction here. So it's going to start rotating clockwise, and the center of mass will be moving upwards as well. So there's going to be motion that starts, and that's what we want to avoid by applying the conditions or imposing the conditions of static equilibrium. So how would we go about solving this problem? Well, we're just going to write down those two equations, right? And in this case, for the force equation, the only forces that will be relevant are going to be vertical forces. You can see there's going to be a vertical force from the weight of mass 1. There's a vertical force due to the weight of mass 2. There's going to be a vertical force due to the weight of the meter stick itself. Then there's going to be a force due to this balance, this fulcrum here. And that force is going to be a vertically upward normal force that is normal to the horizontal meter stick. And then there's going to be a force vertically downward due to M3, due to weight 3. Are you seeing a blurry video? When I look at my preview here, it seems like it's coming through fine on at YouTube at least. So it might just be a local internet issue. Okay, good. Thanks for confirming that it looks fine to you, or at least some of you. Okay, good. So let's take this drawing of the torque balance and now turn that into an actual schematic. So we've drawn the force balance itself. The meter stick has this line here with its weight in the middle downwards. We have the normal force at the fulcrum that's pointing upwards, and then we have our unknown weight 3 and our two known weights, weight 1 and weight 2. So if we wanted to write the equations and the conditions for static equilibrium, one of them will of course be that the sum of those forces has to be equal to 0. So, and that will immediately tell us that this unknown force at the fulcrum, this reaction force at the fulcrum or normal force at the fulcrum, will have to be in magnitude equal to the sum of all the weights that it's holding up, right? That is something that probably in chapter 5 you would have been able to derive. Now the other part of this is the torque equation, and that is going to be new, right? So now we have to make sure that the torque of all of those 5 forces adds up to 0. Now if we want to calculate the torque, we have to pick a pivot. And we established last time that it doesn't matter where you pick your pivot, but if we are going to pick a pivot that we calculate the torque around, we might as well pick it so that it leads to a mathematically easier torque equation. So where would that be in this case? And of course you can see in the text that it's already written there. We'll pick the pivot at this point here, which is at this fulcrum here. And why do we pick the pivot there? Well, that's where we have an unknown as of yet reaction force or normal force. And so if we pick the pivot here, then that will cause this force to not have any torque around that point. And so we can drop it out of our equation. So the only thing that we have left in our torque equation is going to be then the weight 1, weight 2, the weight of the meter stick, all of which we know, and the one unknown weight 3, or the torque due to those weights. So let's write that all down. So we're going to start with the 2 equations. So we have that our forces, the total force will be equal to 0, and the total torque will have to be equal to 0. So in this case, in the vertical direction, that will give us that the weight 1, or minus the weight 1, minus the weight 2, minus the weight of the meter stick, minus the weight 3, plus that reaction force will have to be equal to 0. And that gives us immediately that Fs will have to be equal to weight 1 plus weight 2 plus weight 3 plus the weight. Now for the torque, this will be a torque around the z direction, with the pivot point at the fulcrum. So that will be the torque due to force 1 plus the torque due to force 2, or the weight 2, plus the torque due to the weight. And all of this are going to be torques that work in the counterclockwise direction. So those are going to be positive torques. That's why I'm giving them a positive sign here. Then there's going to be one torque due to weight 3 that's going to be negative. That's a negative torque because it's working in the clockwise direction around this fulcrum. And then of course there's no torque due to Fs because that is exactly where the pivot is. So this will all be equal to 0. And now of course it becomes a matter of plugging in the distances. So the distance from the pivot to force to the weight 1 will be R1. So this will be R1 W1 plus R2 W2 plus R times W minus R3 times W3 will have to be equal to 0. And we're trying to solve for W3 as a function of all of our R, R1 and R2 and the weights. So we'll be able to rewrite this as W3 is equal to 1 over R3 times R1 W1 plus R2 W2 plus RW. And we can plug in those numbers. And when we plug in the numbers for those particular values, we'll get the value for mass 3. And we can actually, since we are given these values in terms of masses, we probably want to go from the weight to the mass. So the mass 3 is the weight 3 over g. So that will be 1 over r3 times r1 times mass 1, because now I'm going to take all of those weights and divide them by g as well. So done, plus r2 m2 plus r times m. And if you plug in the numbers here with r1 equal to 70 centimeters, r2 equal to 40 centimeters, r equal to 20 centimeters to the center here, and then r3 equal to 30 centimeters, then you would find that this mass is, as is worked out in the textbook, is 317 grams. So that's the mass 3 that we have to hang here to cause this to be in equilibrium. And so you see that you have to put a larger mass 3 here than the sum of all of those masses. And that's because, of course, we're closer to the fulcrum. If we had a longer lever arm, then the torque would be larger would be the same for a smaller mass, mass 3. So of course there's a connection here between the mass and the distance away from the fulcrum that we put the mass, as of course you know intuitively must be the case. So now that we have mass 3, we could go back and use this to plug into our expression and calculate the total force on the fulcrum. So why is this a useful problem? Well, I mean, first of all, it's a useful problem because it is nice and indicates, allows you to use the static equilibrium. But why is this a useful device? If we look at the determination of mass 3, if we had an unknown mass that we're trying to determine, we can determine this mass using only distances and other masses. So if we know our mass m1, m2, and m, and we know the distances r1, r2, r, and r3, then we can determine m3. This is different from other kind of mass measuring devices, like with springs or so, where there's always a factor g that we have to explicitly include. And so, whereas here we could measure our distances and our masses to very high precision, much better than we know the value of g. So that means we can determine the mass m3 to a much higher precision as well. And of course, that becomes important in well, let's just say, put yourself in the mind of someone 200 years ago who's trying to sell goods, and they want to, of course, sell. Let's say, for example, if M3 is a mass of gold, you don't want to be affected by a large uncertainty in G if you're trying to determine what mass of gold you actually have that you're trying to sell. You want to have an exact measurement that doesn't depend on the uncertainty in some physical parameters that you have to measure or have your court scientist measure the value of G. So this is a measurement of mass that doesn't depend on measuring G. Okay. Any questions about this problem? It's a fairly straightforward problem. It's one that would be. I'm sure you can see how this could be turned into a very nice final exam problem, because there's many different variations that can be made, and they all and there's many different things we can ask about it. So okay, so let's look at a different problem now. Also one that is a little bit more complicated. The problem of a ladder against a wall. Someone's asking to see the free body diagram here. So I'm going to flash this up for another 10 seconds or so. But then we're going to move on to talking about the problem of a ladder against a wall. Okay, so if we have a ladder that's standing against a wall, one of the things we might wonder about, especially if you're going to climb up on this ladder, is whether there's enough friction to prevent the ladder from slipping. So let's say we have a ladder that's 5 meters long and it's at an angle of 53 degrees, probably a little small for climbing on the ladder, but let's go with it. Let's imagine that the wall is frictionless, so there's no the wall is not going to help keep this ladder up. The wall is just there to provide a force normal to the wall. It's not going to provide any forces along the wall that keep the ladder from sliding down. The wall is frictionless. But of course there's going to be some friction of the floor here, which will translate into a component of the force that is pushing against the ladder towards the wall. Let's assume, for the benefit of whoever is climbing on the ladder, that this is static friction, and so the ladder is not sliding yet, but there is static friction, and this is entirely a problem of static equilibrium. And so we're asking, what is the first of all, what's the reaction force from the floor, from the wall on the ladder, but then also what is the minimum coefficient of static friction for which this static equilibrium will be satisfied. So once again, the problem is, it's a static equilibrium problem, so we're going to use our two conditions of static equilibrium, that the total of all of the forces on the ladder has to be equal to 0, and the total of all of the torques on the ladder has to be equal to 0. So so there will be forces. We already talked about that. There's going to be the normal force from the wall on the ladder. There's going to be the normal force from the floor on the ladder vertically upward, and then there's going to be the friction force, static friction from the floor on the ladder, that is going to be parallel to the floor pointing towards the wall. That's the force that is actually going to prevent the ladder from sliding, right? There's going to be one other force, and that's the weight. Excuse me. That's going to be the weight of the ladder, and that's going to be a force, of course, vertically downward, and that applies at the center of mass of the ladder, so right in the middle. So we're going to introduce some symbols. We're going to call the length L. We're going to call, well, I should go to the next slide, which has all the symbols in it, and frankly, many more angles than are necessary here, but let's go with it. So it's got the length of the ladder L. This is our force, the reaction force to the normal force from the wall. This is the normal force from the floor, which we'll call N, the force of friction, little f, and then the weight W. So those are all of the forces in this problem. So let's start by writing down the first condition of equilibrium, which is that the sum of all the forces will have to be equal to 0, right? So let's look at that in the x direction. This component is horizontal, big F and little f is horizontal. So the sum of those two will have to be equal to 0. Or in other words, little f and big F are going to have to be equal in magnitude. If we write that down, so ladder against the wall. So in the x direction for fx, we find that little f will have to be equal to big F. The magnitude of the force of friction will have to be equal to the magnitude of the normal force from the wall. The next equation that we can immediately write down is the force condition in the y direction. The sum of the normal force from the floor and the weight of the ladder will have to be equal to 0. So that means that the normal force will have an equal magnitude to the magnitude of the weight. So N, so Fy gives us as a condition that N is equal to the weight, right? So now there's one other condition, and that's the condition due to the torque. And again, we have some choice here. We can choose where to place our pivot. We can put the pivot at the point of contact with the wall. We could put the pivot at the center of the ladder. We could put the pivot at the point of contact with the floor. We could even put the pivot at some entirely different point. I mean, if you want to, you could put the pivot at the corner between the floor and the wall. I don't know why you would do that, but if you wanted to, you could do that. Let's pick a pivot at the point that's most convenient. And what's going to be the most convenient point? Well, it's going to be the point where the most, in this case, where the largest number of torques disappear because of the choice of the pivot. If we pick the pivot at the point of contact with the floor, now I don't have to worry about two torques, the torque due to the horizontal force of friction and the torque due to the normal force. Both of those are going to be trivially zero because of the fact that they apply at the pivot. So the only torques I'll have to calculate is the torque due to the weight and the torque due to the normal force at the wall. So now it becomes a question of what is the magnitude of those torques due to the weight and due to the normal force at the wall. And so what we're going to do is we're going to first think about the sign. So the torque due to the weight is going to be clockwise, so it's going to be negative. The torque due to the wall, the normal force at the wall, is going to be counterclockwise around the pivot, so it's going to be positive. So at least they're opposite in sign, which is good because that will help us have the torque condition be satisfied, right? So what's the sign of the torque? Or what's the magnitude of the torque? So this is where we have to do a little bit more math. So we can do two things. Either we can take the we could do three things, right? For calculating the torque, we can use just the regular formula, which is the distance to where the force applies. Let's apply it to the weight here, for example. So this is the half of the length times the weight times the sine of the angle from the position vector all the way down to the weight. So that's our theta w here. We could also say we're going to take the perpendicular distance to the line of action, which is going to be just the distance L over 2, but times cosine beta to get the perpendicular distance, which is going to be to the point where the weight, the line of action, would go through the floor here. Or we could use the distance to the point where the force applies times the perpendicular component of the force. And the perpendicular component of the force is going to be the component of the weight that's in the perpendicular direction. So I'll let you choose what's easiest. In my case, for me, I think the easiest is to use the distance to the line of action, where on this figure you can immediately see that that's beta, cosine beta times L over 2. So we're going to have as a torque equation that the torque due to the weight will be the weight times r perpendicular, so that's going to be the weight times L over 2 times cosine beta. And that has to be equal and opposite to, and equal in magnitude to the torque due to the force of the wall, the normal force of the wall on the ladder. So again, I'm going to do the same thing here. I'm going to take the distance to the line of action. And the line of action is the horizontal line that goes through the top of the ladder here. So that distance is L times the sine of beta, because now it's the opposite. So L times the sine of beta times the force is going to be tau F. So that's tau F. So that's this force times L times the sine of beta. So let's look at that again. We have that the torque of the weight and the torque due to the force, due to the normal force, have to be equal and opposite to each other in a vector quantity. So that means that their magnitudes are going to have to be equal to each other. And I can write down the torques as the product of the force and the perpendicular distance to the line of action. The force and the perpendicular distance to the line of action, both for the weight and for the normal force. And ultimately I end up with an equation that is that W L over 2 cosine beta has to be equal to F times L times sine beta. Okay, so let's think about what we're trying to do here now. Let's go back to the problem here. We're trying to determine the normal force that the wall exerts on the ladder, because that will give us then the friction force that we have here, right? Because those have to be equal and opposite. So the normal force due to the wall, that's our F. So if we solve for F, we'll find that F is, what do we have here? W over 2, and then cosine over sine, that's the cotangent of beta. So that's the force, normal force. So that's going to be also the force of friction due to our first condition here. And then our normal force of the floor is equal to the weight, right? So now we have all of our forces determined. We have our force of friction determined just in terms of the weight and the angle beta. We have the normal force determined just in terms of the weight, and so on. All of our quantities are determined. So then let's go back to the actual question. What is the minimum coefficient of static friction at the interface of the ladder with the floor? So now we have to verify our assumption, and our assumption was that there's static friction here, right? This is technically Fs. So Fs must be less than or equal mu s times n, or mu s must be at least Fs over n. And we know what Fs is. It's equal to F, or it's equal to W over 2 cotangent of beta. And we know what the normal force is. That's the weight. So we find that this must be at least 1/2 times the cotangent of beta. And obviously this is just math. Obviously we would fill in the numbers. So that means that in this case, if that's 53 degrees, this must be at least 1/2 times the cotangent of 53 degrees. I'm clearly not doing very well here today. Yes, okay, 53 degrees. And if we plug in those numbers, calculate what the actual magnitude is of the mu s, we would find that mu s has to be greater than 0.377. If you just plug in the cotangent of that number. So as you can tell, and as Jonah points out in the chat, it doesn't depend on the weight. It doesn't depend on the length of the ladder. The only thing that this minimum coefficient of friction depends on is the angle with which the ladder is balancing against the floor, against the wall. So there's nothing that matters to this except for the angle. Now, there's an extension of this problem, and that's not one that is covered in as an example in the textbook. But of course, there will be something that might change if you start climbing on this ladder, right? All of this assumes that there's only mass due to the ladder itself. If you start climbing on this ladder, and let's say you're further down on the ladder here, you will start changing those force balances, and in particular the torque balance. And so if you start climbing up higher and higher and higher, the required coefficient of static friction will change. So that's something that you could do as a homework problem, or as a self-study problem, is to calculate what would happen now if you are standing on this ladder somewhere, let's say between 0 and L, and what is the coefficient of static friction that's required if you're somewhere on that ladder. Not necessarily, as in this case, that there's no weight on this ladder. If you are on this ladder, then this condition will depend on your position on the ladder. Another problem that is interesting, I would say, to do is what happens when you actually reach the height where the coefficient of friction can't sustain you anymore. Then suddenly we're in the case of kinetic friction. Then this becomes a chapter 11 problem, right? Then this is a problem on angular momentum. Now we have the ladder that is sliding down. There's still going to be a normal force here. There's still going to be a normal force here. Actually, this normal force is not going to, well, it is going to change because there's going to be some vertical acceleration. There's going to be some angular acceleration. All of that becomes a complicated problem to solve. But again, there's ways we can extend this problem. Don't do that part where it actually starts to slide. Don't do that at home, because that actually is more appropriately treated with some more advanced methods. So. Okay, any other questions on this this ladder problem? Okay, if not, then let's go to a few more examples. I'm not going to go in detail on those, but one additional problem is this problem of that's also covered in the textbook is this hinged door. So we have a door that has a uniform mass. So the center of mass is right in the middle of this this door, and it's hanging by two hinges. Of course, a very common situation for a door, unless of course unless your door is dragging on the floor here, when there will be another point of contact. But if the door is just hanging from the hinges, there's going to be a force here, a force here. In this case, contrary to the ladder leaning against the wall, now there will be a vertical or a component of the force that can be along the direction of this point of contact, right? So this is the difference between a frictionless contact point that we have here of the ladder against the wall and a fixed hinge, which doesn't just provide a force in the horizontal direction, but can also provide a force in the vertical direction. So we're going to have a force at point A that is going to be trying to so the force of the wall on the door is going to be pulling the door towards the wall. In this case, at point B, it's going to be pushing the door away from the wall to counteract the negative torque of the force of gravity, the weight of the door, with a positive torque due to the force from the hinges. So if we look at that, we've got the forces in hinge A and the forces in hinge B. We have the center of mass here, which is where the force, the weight applies. Again, we can calculate the balance of the forces. So since the only horizontal forces are AX and BX, those are going to be equal to each other. AY and BY will add up to be equal to W, and the only other thing we have to solve from is now the torques. And so in this case we can put the pivot at point A or point B. That would be the easiest because AX, AY and BX, BY are the unknowns here. I wouldn't put the pivot at the center of mass because then we're not gaining anything, right? Then we don't gain as much because we know the weight, so we can actually calculate the torque there easily. It's the torque in point A or point B that is going to be convenient. So the question that Isaac is asking is, why are AX and BX opposite to each other? Well, they have to, because there's no other, because there's no other horizontal forces here, right? And the sum of all of the horizontal forces has to be equal to 0. So this isn't necessarily a requirement because of the torque. It's because of the force condition. So the horizontal component of the force, the x component of the forces, will have to add up to 0. So that means that AX and BX have to be in opposite directions, or of course they could be 0. But if they're 0, then of course that doesn't work with the condition for the torque. I hope that explains things. So I'm not going to go through the actual calculation here, but you could calculate the forces on the hinges now from the third condition, which is the torque around point A, which will now have a component due to Bx and a component due to the weight. And finally, this is also a common example or a common problem on tests, which is this shop sign that's hanging off the end of a rod. It's also, of course, a very common statics problem in calculation of trusses in mechanical systems and structural design. So we have a rope that is, or a cable that is hanging here. So there will be tension in this cable. There's a weight of the sign itself at the end of this rod. There's the weight of the rod itself. The rod itself has a weight that can be thought of to be concentrated in the center of mass. So it's going to be at the center of this this rod. There's going to be a fixed point here where the rod is attached with this hinge. This is very similar to the hinge of the door in that it's not a frictionless point of contact. It's a point of contact that can have both, and that will have both, a normal force that pushes towards the rod and a vertical force that is going to prevent the rod from sliding up and down. So again, we can write down all of those forces. We can calculate. We can draw this in a free body diagram. We can, let me see if I can. I guess I don't really have. Yeah, this isn't Zoom, so I can't draw on the screen here as easily. But we will have on the system of interest, which is the rod and the sign that's attached from it. We'll have two forces at the point of contact here. We'll have the two forces of the weight, and then we'll have one force due to the tension. And so if we wanted to calculate the tension in this cable, then we probably will want to start by putting the pivot at the hinge, which is where we have the two unknown forces, and then work our way up from there to solving for the tension. Julian is saying it seems like the forces tend to cancel out in these questions, and all that's left is the torques. Yes, but to some extent, the torques are also the things that cancel out. Everything has to cancel out. That's the requirement for the static equilibrium conditions. It just happens that we're splitting this up in a way that typically makes it easier to see how the forces are canceling, and it's not as easy to see how the torques are canceling because we don't tend to think in those vector quantities. But if you think about it here, for this hinged door, if we calculate the torque around the pivot point A, the torque due to Bx and the torque due to the weight have to cancel. And you can sort of see that one of them will point in one direction, the other one will point in the other direction. That's also a way in which you can see that the torque in B, or the force in B, has to be towards the door. So everything will have to cancel, and it just happens to be that we've been talking about forces for this entire semester, that this is already coming naturally to you, and you can immediately identify why it's canceling. Okay, this was the last problem. Well, I guess this one here was the last problem, and on static equilibrium, and so on Monday we'll start with stress and strain, elastic modulus, Young's modulus, volume modulus. That's more of um, a descriptive problem, a descriptive section. So we probably are going to go through that fairly quickly, and then I imagine on Wednesday we'll talk about gravity, um, and then on Friday or maybe on Monday with special relativity. Okay, have a good weekend, and talk to you all on Monday.